I'll also be recording on my end just in case. Okay. Oh, not through Zoom though, through a separate software.
Okay.
But yeah.
So let's take a look at the actual book and start with the nose cone and work our way down.
Okay, you should. You can't pull it out. But you can't pull it out. Yeah.
So here's our nose cone on the upper body tube. So our original payload housing that we did for the practice launch, the fit between the 3D printed part and the actual payload itself was a little bit too tight, and so we sent the parts for that to get water jet. Unfortunately, the water jet, their machine is currently broken. We were supposed to get the parts this week to put it together, but we did not achieve that, and so we don't actually have the assembled payload in here. But I do have the 3D printed housing. So this, you can see the square part for the payload to be inserted. We will have a aluminum 1/4 inch section on here, and then this will be permanently inserted into the nose. Then we'll insert the payload, and then we have this part is the removable housing, and we will have another 1/4 inch aluminum plate on the top here, and that's what our eye bolt will attach to for the parachutes, and then we will have the 3/4 inch rod coming through here. A couple things we also learned from the practice launch is on here. You can see we have some chamfers on the edges here, and that's to help with the alignment onto the payload itself, because we'll be reaching down into the upper body tube and putting on. Just makes the alignment a lot easier.
Okay, is TCG secured? How is that secured in the nose cone?
Through epoxy.
Okay. Your nose cone doesn't weigh a lot, so this. Is there anything else holding, say, the nose cone to the coupler?
Yeah, that'll also be epoxy.
Okay, and what's the coupler made of?
The coupler is the blue tube, and then the nose cone is the carbon fiber.
Okay, let's do the nose cone as the coupler.
So the coupler that connects the nose cone and the upper body tube, right?
Right.
Yeah, so it was all just manufactured out of carbon fiber from the company.
Oh, okay, so it's a one-piece nose cone.
Yeah, it's a one-piece nose cone.
Okay.
And then we're epoxying the coupler and the upper body as well.
Okay. The concern is that when you try to epoxy to ETG, you don't get a chemical bond. You're just relying on the surface imperfections to hold things.
Yeah, so we also did a like hydraulic testing press with a PETG centering ring and a body tube with the epoxy. Did we get the results?
The PETG ended up failing first. It was 7.
I'm sorry, it's poison.
So yeah, I was the one who did the testing. The centering ring failed before the bond between the bond between the centering and the tube, it failed at the centering failed at about 7,000 pounds of force.
Okay.
Do you have any other questions about the payload housing, payload, or nose cone?
No, yeah, yeah. So, so next we can see, this is going to be airframe.
Yeah, so this is our main chute. It's not completely folded up at the moment.
Right.
We just did some checking for the cords and the parachute to determine if there was any imperfections. And then this is our shock cord. And we're gonna have both in a deployment bag, and it sits right in here. Goes up in there, and then the systems bay. This is the systems bay. It'll attach through these U-bolts down here, which will then be connected to the upper body tube. So the parachute will go in between, and then it'll slide in. Yeah. And then, so we have the two holes cut out for the altimeters and also the key switch. So yeah, they're 180. Yeah. And then the drogue chute. Here's the drogue chute. It's in its deployment bag. This is the drogue chute we're using. We purchased a new shock cord a couple days ago, just because the one we used previously seemed to have a little bit of a imperfection. So we purchased that, and so we placed this in here, which the systems bay goes into. Yeah, and so it's not just friction fit. We also are going to have to put in 6 shear pins around the side to hold it together so that the CO2 ejection has to feed the friction and the shear pins.
What's that shear pins?
Oh, so number 4.
Okay.
Yeah. And so then this is the rest of the body, lower body, and the fins. We already did all the fin fillets in the clock, and so it's all spray painted. But if you wanted to come over.
That would be really, really bad. Let's see. Can you see down?
Yeah.
Can you shine a light? So that is the top of our motor. Yes, that's the top of the motor mount. So you can see the aluminum plate. Yeah, I'm sticking my hand in the way. But you can see the aluminum plate with the eye bolts. So that's the same aluminum. There's another aluminum plate on the other side that will give additional strength and also help protect the PETG from any sort of heat from the forward closure. Mainly just acting as a sink, but so we have the eye bolts. There are 2 lock nuts that are tightens and on the other side of the aluminum plate.
So there's, we have the eye bolt that goes to one aluminum plate, and then we have 2 nuts, and then we have the second aluminum plate, and then the motor
will screw
butts up right to that second aluminum plate.
Let's see, this motor has to go already in, right?
Correct. Correct.
And it would not be a bad idea to stick some epoxy here.
Actually.
On the threads. Before you tighten your lock nuts.
Yeah, it's actually a good point. So we should be able to do that now because we should still be able to pull out the aluminum plates. So,
Yeah.
a good idea. And then, yeah, so the aft end, so this is our motor mount tube, this motor sleeve. And then this is one of our 4 center rings.
Okay. Your previous design showed a little bit of space between the forward end of the motor mount tube and that forward bulkhead.
Yeah,
Do you have that space in this design, or it's butted right up against it?
Yes, we do. It's, I don't know if
Okay.
there's a good way to measure it. I hate to say it. But it's a couple of inches. So what are we doing?
Okay. I'm curious why you are using that eye bolt up at the forward end as your thrust transfer instead of having a thrust plate in the back end.
What do you mean by a thrust plate?
plate.
So we have the motor goes directly into one of the aluminum plates.
That's right up against one of the aluminum plates, so.
Well, did you have the motor casing there?
Yes, let me just go grab it.
Okay, look at the aft enclosure.
Mm-hmm.
You can see that it's actually got a little bit of ridge.
Yes.
And its diameter is a little bit greater than the motor casing, the rest of the
Yes,
motor
it is.
casing. And what the company has in mind there, the standard way to do it, is you have like an aluminum plate that's the diameter of your motor casing that pushes against.
Interesting.
So that would go just like right here. So instead of it butting up to this motor sleeve, it butt up to an aluminum plate right here.
Is that?
Right.
Okay.
Oh, interesting. That's not something I looked at, actually.
Yeah.
And something I would strongly recommend,
Mm-hmm.
will make people feel a lot more comfortable as you're designing with me, is you can actually just buy commercial aluminum thrust plates. I think Apogee sells them. And if you just set one there at the aft end of your rocket,
Okay.
it would give you quite a bit more strength at a place where I'm kind of concerned about it.
Okay. Okay. Yeah, we can certainly look into that. I mean, there's nothing saying that we couldn't have both, to be fair. But if nothing else, I'll definitely pass that on to next year.
Well, yeah. Looking at it, it looks like you could just. It looks like you've got space to just.
Yeah, we should
take
have.
a quarter-inch aluminum thrust plate and put it there.
Yeah, you're right.
Yeah, we can implement that pretty easily.
Yeah, I would highly recommend that.
Yeah. Okay. Okay. There's one of you. Fins now? Do you have any other questions for me? Actually, I should ask first.
Yeah. My question also in general to everybody, because I'm not entirely. I frankly am not good with names, so but
Fair enough.
another question I have is the .log file you showed earlier showed 3 railable buttons.
Oh, yeah.
Why?
Well, we thought it'd be important to have 2 at the lower and then 1 at the upper body. Because we thought 2 was a minimum to have, and so we thought maybe we should add 1 more at the upper body too.
And I would actually suggest not doing that.
Okay.
You've got 2 widely separated rail buttons, and so they should be placed strong.
Both on the lower body?
The 2 on the lower body.
Okay.
Yeah. Putting a 3rd one on typically does more to cause added friction on the rail if you've got any kind of microscopic alignment issue
Okay.
than anything else.
Okay, that makes sense.
Okay, yeah, you guys are actually, of the ones I've looked at this year, you guys are the ones who are most prepared. I've looked at others that had a tiny title of fiberglass they were showing me.
Oh no.
Purposes to actually epoxy together. I've told those teams that they are running a little. And yeah, this looks very good.
Thank you.
So yeah, actually those suggestions.
Yeah.
Beyond that, I'd say we're pretty much starting to go. Where you should go from here is go ahead and get that recording to Ezra.
Yeah.
And also go ahead and send as an attachment
The
the
PDF.
slides from your presentation.
Yeah, of course I'll do that.
And mention the issue, the real part that we were not recording.
Yeah.
That's how we report. So there's quite a few questions that came up during that.
Yeah.
That I didn't want to ask again just because we're recording now.
Okay. I also wanted to mention that I found the email from Aerotech, and then they said that we can expect a temperature of about maximum of 250 degrees on the case after the total rotor burnout, which is much lower than the melting point of the phenolic tube and PETG.
The PETG melts at about
260.
260.
C. This is F.
260.
Okay, so that was
Yeah.
250 thermal.
Yeah.
Actually, that seems pretty good.
That's what they.
Okay. And you actually, the issue isn't actually the melting point, it's the glass transition temperature.
Yeah, that is true.
And I don't know where that is, but it is somewhere below 80 Celsius. And so, yeah, it won't be melting, but there won't be much strength from the accelerators at that point.
Yeah, we're not relying on it for strength, though. Sorry, go ahead.
Well, insofar as keeping the motor stable in the airframe, yes, you are.
Yes.
That's fair.
And that's actually another reason for a thrust plate, because a properly sized thrust plate is an aluminum semi-ring back there.
Yeah.
So you do that, and you stop relying on the strength of the P2C.
Okay, yeah. Yeah, okay. Yeah, we'll definitely implement the thrust plate.
Okay. So, yeah, do you have any questions for me?
No, not at the moment.
No.
Okay.
Nothing I can think of.
All right. Yeah. Thank you so much. I look forward to seeing you as well.
Sounds good. Thanks a lot.
Thank you.